a flyback converter. Okay, so the flyback converter circuit diagram is shown here with a single switch topology, and it acts buck boost nature, and depending on the turns ratio N1 and N2, the voltage gain of this flyback converter is D by 1 minus D into N2 by N1 duty ratio. The purpose of this experiment is essentially we want to know the what is the load voltage if I change the duty ratio of the main switch is connected on the primary side. And in addition to this one, whenever there is change in duty ratio, load voltage will change according to this equation. But there is one more factor which is available, N2 by N1 ratio. So depending on this one, the D by 1 minus D characteristic is going to either shift upwards or downwards. In the laboratory prototype, the transformer turns ratio taken as 1:1. So in that case, this will give only buck boost conversion, that is load voltage is less than the supply voltage, or load voltage is greater than the supply voltage, which is boosting action. So you can see the bucking and boosting in the fixed duty ratio operation, but in the closed loop operation, this prototype module is designed for the bucking operation. So we will be demonstrating the closed loop operation for a load voltage of 5 volts, whereas the supply voltage is going to vary anywhere from 6 to 18 volts, which is nothing but 12 volts is a nominal voltage plus or minus 50%. So 12 minus 6 is 6 volts, 12 plus 6 is the 18 volts. So we will be demonstrating the functionality of closed loop converter voltage regulation. Load voltage is regulated at a 5 volts, whereas supply voltage is changed from 6 to 18 volts, where 12 volts is the nominal voltage. Another thing is we will also demonstrate what is the dependence of load voltage against the change in the load resistance, as well as we will also demonstrate what is the impact of load voltage if there is any change in the supply voltage. Since it is operated under closed loop operation, whenever there is a change in the load or whenever there is a change in the supply voltage, in both the cases the duty ratio of the switch is going to change in order to ensure the constant voltage regulation. So in this experiment, we set the input voltage, we measure the duty ratio of the switch, and we will also measure the output voltage in the experiment. This is the total system setup. You see, this is the supply voltage. We set the supply voltage from the 6 volts. Right now it is set to 6 volts. I can set to nominal value, that is 12 volts. Okay, so I can also increase this voltage to up to 18. So firstly, I will set this voltage to 12 volts. So right now voltage set to 12 volts. Okay, when I set the voltage set to 12 volts, you can see the load. The load is connected in between these two terminals. So the load is roughly we have put the load which corresponds to very small load. You just show. Okay, current is roughly around 80 milliamperes. Current is around 80 milliamperes. Okay, so for this load, this is corresponding to light load, and by setting the light load, now I will be demonstrating the load voltage regulation. The load voltage reference is set to 5 volts. We can see 5.06 volts. Okay, so this load voltage also you can see on the scope. The channel 1 is the duty ratio, and whereas channel 4 is the load voltage. So from the measurements display, you can see two important aspects. One is the duty ratio, another one is average voltage. Next one is switching frequency. So this switching frequency closely according to the experimental prototype, it is closely 29 kilohertz. Okay, so this is a PWM signal which is coming from the gate and source. So in this prototype, we will see the input, the maximum voltage that it can vary 0 to 30. This is the switch. This is a switch. It is IRF switch. Okay, and this is a transformer, 1:1 transformer, and internally there is a diode is connected, and these are the terminals, load terminals. Okay, and this portion corresponds to PWM generation using the TL494 IC. This TL494 IC is a device, is a IC which internally has a triangular ramp generator, and we can connect the controller. The controller essentially generates a reference voltage, and the internal comparator compares the reference voltage with the triangular ramp, and it generates the suitable duty ratio. So PWM duty ratio signal that is seen here on the scope. So at this moment, the converter is running under closed loop operation, and for a input voltage of 12 volts, for a load voltage reference of 5 volts, the duty ratio is, nominal duty ratio is close to 23.6. If I change either supply voltage or load, this duty ratio will change according to the variation in the input voltage or load, such that the load voltage maintains almost close to 5 volts. Now the load source voltage is changed from 12 to 18. So I am setting the source voltage to 18. When I change the supply voltage to voltage from 12 to 18, the closed loop operation of the converter or control loop is going to change the duty ratio, which is driving the this switch as to change from 23% duty ratio, which was the case. And if you look at this load voltage is, you can see 5.06, whereas in the previous case it is 5.08. Now this value is almost constant, but there is small change in the second decimal digit. Whereas the duty ratio, earlier it was the nominal duty ratio at 12 volts supply voltage, it is around 23%. Now it is reduced to 15%, so that output voltage is almost maintained constant. Next, I will change the supply voltage from 18 volts to 6 volts. In this case, duty ratio variation is going to change from 15% to higher value. That we will see little later on the scope. So now the source voltage is 18, corresponding closed loop duty ratio is roughly 15%. Corresponding closed loop duty ratio is 15%. Here you can easily see, and whereas load voltage is 5 volts. Okay, but now I am changing the input voltage from 18 to 6, keeping the load constant. Now I set the load source voltage to, which is supply voltage is 6 volts. Now let us see, earlier duty ratio is 15%. Now you can see the duty ratio is changed from 15 to 48.4% in order to maintain the load voltage of 5 volts. So from these measurements, we can easily understand that whenever there is any change in supply voltage, the duty ratio, PWM signal duty ratio is continuously adjusting, such that the load voltage is maintained at close to 5 volts. We will be demonstrating how this converter is going to regulate against change in the load. So to demonstrate this, first I will set the supply voltage to 12 volts, and load current, it is drawing roughly 80 milliamperes, while its load voltage maintained at 5 volts. Whereas the duty ratio is maintained at 23% to maintain the load voltage of 5 volts. So if I want to change the load, this is a load bank. By means of this turning on, switching on these knobs, we can change the load. So at this moment, the load corresponding to on the meter load current is roughly 80 milliamperes. Now I am putting a load on the system. So load on the system. When I'm increasing the load, you can see the load current is changed to roughly 120 milliamperes, and at that point of time, load voltage maintained at 5 volts only. Okay, but if you look at the duty ratio initially it was 23%, but since I have increased the load, duty ratio has to increase to maintain the load voltage. You can see duty ratio changed from 23 to 30.2%. This is essentially to regulate the load voltage, which is constant reference voltage set to 5 volts. So if I increase the load and decrease the load, immediately you can see the variation in duty ratio. To show this fact, right now the load is higher load, that is 120 milliamperes. Now I am reducing the load from 120 milliamperes to 80 milliamperes. You can see the duty ratio is going to change from 29 to lower value. So the lower value set reference is duty ratio is close to 23%, whereas in the higher load case it is equivalent to 30% of duty ratio, but when you decrease the load it is settling to 23.5%, but in any case it is maintaining the load voltage of 5 volts.
Input voltage is set at 6 volts. The duty ratio is 47.
Now please record the observations in your notebooks. Here firstly we are recording the readings for closed loop operation. So we will be varying the input voltage and we will see the change in the duty ratio.
Load voltage of 5 volts.
Input voltage is set at 6 volts. The duty ratio is
Hello. Now we will record the readings. Please note down the observations in your copies. And firstly, we will note down the observations for closed loop operation. In this, we will vary the input source voltage and we will see the variation in the load, we will see the variation in the duty ratio to keep the output voltage constant. So make a table of 3 columns. In the first column, we will write the input source voltage. In the second column, duty ratio, and in the third column, there will be load voltage.
%, and output voltage
to 23.5%. So the lower value set reference is duty ratio is close to 23%, whereas in the higher load case it is equivalent to 30% of duty ratio, but when you decrease the load it is settling to 23.5%, but in any case it is maintaining the load voltage of 5 volts.
Input voltage is set at 6 volts. The duty ratio is 47.6%, and output voltage is 4.955. Now I'll change the input voltage to 7 volts. Duty ratio is 40.9% and output voltage is 4.956. Input voltage 8 volt. Duty ratio is 35.5%. Output voltage 4.961. Input voltage is 9 volt. Duty ratio 31.7%. Output voltage 4.965. Input voltage 10 volts. Duty ratio 28.6%. Output voltage 4.966. Input voltage 11 volts. Duty ratio 25.8%. Output voltage 4.967. Input voltage 12 volts. Duty ratio 23.6%. Output voltage 4.971. Input voltage 13 volts. Duty ratio 21.8%. Output voltage 4.971. Input voltage 14 volts. Duty ratio 20.3%. Output voltage 4.971. Input voltage 15 volts. Duty ratio 18.9%. Output voltage 4.971. Input voltage 16 volts. Duty 17.8%. Output voltage 4.974. Input voltage 17 volts. Duty 16.9%. Output voltage 4.971. Input voltage 18 volts. Duty 15.8%. Output voltage 4.975. The previous table was for input voltage variation, where the load was fixed at 80 milliampere and the input voltage was varied from 6 volt to 18 volts. Now in the second table, we will keep the input voltage fixed at 12 volts and we'll vary the load, and we'll see how the the output current or load current varies, the duty ratio and the output voltage.
Also note down the output current in the previous table, that is
So for the first reading, the load is set at 10 milliampere. Duty ratio is 6.5%, and the output voltage is 4.9 milliampere and voltage 4.975. Output voltage 4.974. 975. So for the first reading, the load is set at 10 millishow and the load voltage was varied from 675. Input voltage 18 volts, duty 15.8%, output voltage 4.975. The previous table was for input voltage variation, where the load was fixed at 80 milliampere.
here note down the load was fixed at 80 milliampere.
And the input voltage was varied from 6 volt to 18 volts. Now in the second table, we will keep the input voltage fixed at 12 volts and we'll vary the load, and we'll see how the the output current or load current varies, the duty ratio and the output voltage. So for the first reading, the load is set at 10 milliampere. Duty ratio is 6.5% and the output voltage is 4.980 volts. Now the load current is changed to now the load current is 20 milliampere. Duty ratio is 14.3% and output voltage is 4.975 volts. Now the load is again changed to 50 milliampere.
Ma'am, there is no audio, ma'am.
Due percent. Output voltage 4.971. Duty 15.8%. Output voltage 4.975. The previous table was for input voltage variation, where the load was fixed at 80 milliampere and the input voltage was varied from 6 volt to 18 volts. Now in the second table, we will keep the input voltage fixed at 12 volts and we'll vary the load, and we'll see how the the output current or load current varies, the duty ratio and the output voltage. So for the first reading, the load is set at 10 milliampere. Duty ratio is 6.5% and the output voltage is 4.980 volts. Now the load current is changed to now the load current is 20 milliampere. Duty ratio is 14.3% and output voltage is 4.975 volts. Now the load is again changed to 50 milliampere. Duty ratio is 20.2% and output voltage is 4.970. Load current now is 70 milliampere. Duty ratio has changed to 24.8%. Output voltage is 4.964 volts. Load current is 100 milliampere. Duty ratio is 28.5% and output voltage is 4.96 volts. Load current now is 150 milliampere. Duty ratio is 34.8% and output voltage is 4.954 volts. Here we'll study the behavior of flyback converter in open loop. So Using this knob, we'll change the duty ratio. We have fixed the input voltage at 12 volts, as you can see here. So now for a fixed input voltage of 12 volts and a load of 20 ohms, we'll change the duty ratio and see how the output voltage varies. The duty ratio now is at 6.6%. The output voltage is 587 millivolts. And the load current is
30 milliampere.
Now we'll change the duty ratio to 10.4%. The output voltage has changed to 1.03 volts and the load current is
50 milliampere.
Now the duty ratio is again changed to 15.2%. The output voltage is 1.574 volts and the load current is
80 milliampere.
Now the duty ratio is 20.3%. The output voltage is 2.152 volts and the load current is
110 milliampere.
Duty ratio now is 25.3%. Output voltage is 2.736 volts and the load current is
140 milliampere.
Duty ratio now is 30%. Output voltage is 3.303 volts and the load current is
170 milliampere.
Duty ratio 35.2%. Output voltage is 4.268 volts and load current
225 milliampere.
Duty ratio is 40.1%. Output voltage is 5.316 volts and load current
270 milliampere.
Duty ratio 45.5%. Output voltage is 6.694 volts and load current
340 milliampere.
Now the duty ratio is changed to 50%. Duty ratio is 50.2%. Output voltage is 8.08 volts and load current
410 milliamperes.
Duty ratio is now 55.4%. Output voltage is 9.69 volts and load current
510 milliamperes.
The duty ratio is now changed to 60.2%. Output voltage is 11.692 volts and load current is
600 milliamperes.
Now we'll take similar readings for light load. That is the load resistance is set at 70 ohms. So here the duty ratio is 5.8%. Our voltage is 994 millivolts and load current
10 milliampere.
The duty ratio is now changed
Audio is lagging and
to 10.4%. The output voltage is 1.9.
Sorry, क्या कह रहे थे?
It's lagging. I mean, it's not coherent. Hello? Hello? It's not coherent. lagging.
Hello.
Hello.
Hanji.
The video is not coherent. It's lagging.
Okay.
Ma'am, can you please repeat this reading?
Okay. I will rewind the video.
Can you post it on in the file section? Hello.
Hello. Yes.
File section. This video. Can you upload it?
Which section?
I mean, can you upload this video in the Microsoft channel or somewhere?
No, no, no. No.
Okay.
Duty ratio is now 55.4%. Output voltage is 9.69 volts and load current
510 milliamperes.
The duty ratio is now changed to 60.2%. Output voltage is 11.692 volts and load current is
600 milliamperes.
Now we'll take similar readings for light load. That is, the load is or the load resistance is set at 70 ohms. So here the duty ratio is 5.8%. Output voltage is 994 millivolts and load current
10 milliampere.
The duty ratio is now changed to 10.4%. The output voltage is 1.93 volts and load current is
25 milliampere.
Duty ratio is now 15.1%. Output voltage is 2.94 volts and load current is
40 milliampere.
Duty is now 20%. Output voltage is 3.95 volts and load current is
55 milliampere.
Duty ratio is 25%. Output voltage is 5.045 volts and load current
70 milliampere.
Duty ratio 30.3%. Output voltage 6.154 volts. Load current
90 milliampere.
Duty ratio 35.2%. Output voltage 7.179 volts. Load current
110 milliampere.
Duty ratio is now 40.3%. Output voltage 8.23 volts. Load current
120 milliampere.
Duty ratio is 45.3%. Output voltage 9.312 volts. Load current
140 milliampere.
Duty ratio 50.5%. Output voltage 10.42 volts. Load current
160 milliampere.
Duty ratio 55.7%. Output voltage 11.54 volts. Load current
170 milliampere.
Duty 0.1%. Output voltage 12.924 volts. Load current
190 milliampere.